Good evening and welcome to GMAETS 41 YouTube channel. In our class today, I'll be taking you through development of atomic theory. Now you can see that we've got the screen being shared because I'll be using this format of teaching tonight. Under development of atomic theory, part 1, one of our major focus is to give attention to discovery of atomic particles and some things that are related to the atom. For example, the very first atomic theory, which scientist is responsible for that? And what should we know about the theory? Which scientists discovered the proton? Which scientists discovered the electrons, the neutrons, the nucleus, the charge to mass ratio? Which scientists measured it? What about the charge of an electron? Which scientists measured it? How did the scientists even go about determining all of these things that have been mentioned? So that is one of the major focus of our class today. When dealing with development of atomic theory, there are key concepts, about 8 of them that a student wants to give attention to. First, to talk about John Dalton's atomic theory. You're expected to know about them. Discovery of the protons and the neutrons, you need to know about them, as well as discovery of electrons. You also need to give attention to the cathode ray tube. You need to give attention to it, very important. So there are about 8 main points that you should give attention to when dealing with this topic. So without wasting time, we are going to get to business. I will share the screen and it's going to display at your end. Are you following right? The first area we are giving attention to is John Dalton's atomic theory. Dalton is known as the father of the atom. Let us hear from him as regards his atomic theories. There are 5 of them. I would like to give attention to them quickly.
This is the GMAETS or electronic. To start with, we look at John Dalton's atomic theory. In 1808, John Dalton proposed the first experimentally based theory of atomic structure. He later became known as the father of atomic theory, even if some of his theories have been modified. Quickly, we have 5 of John Dalton's atomic theory. At the point here, we're going to consider them. We're also going to look at those that have been modified and why they were actually modified. We have them in the board. Number 1, all elements are made of small indivisible particles called atoms. Yes, it is true. All elements, they are made of atoms. However, the discovery of subatomic particles, as well as atomic particles, like protons, neutrons, electrons, they are atomic particles. We talk about the subatomic particles, where we look into things like the cleaners, the neutrinos, the positron, the quarks. We consider that at the outset of this course. Remember that. So the discovery of these atomic particles and then subatomic particles shows that yes, all elements contains atoms. No argument, but this atom likely could not be the smallest particle of an element. Let's look at the second theory. Atoms can neither be created nor destroyed. Now you take note that I start this first one, this second one also started, and even the third one. Those ones start are the theories that have undergone modification. Atoms can neither be created nor destroyed. This is true under ordinary chemical reaction. When you move over into nuclear reaction, radioactive reaction, it has been proven that atoms can be created and can also be destroyed. Let us quickly consider a situation where you make aluminium-27, which is not radioactive, but through artificial radioactivity, by bombarding it with an energetic particle, it can produce another atom. Quickly, let us look at it. Aluminium-27, that's atomic number 13, aluminium. If you bombard it with neutron, what are you going to get? During the bombardment, aluminium will emit alpha particle, and of course we know that alpha particle is helium atom. So we're going to have 4, 2, which is helium atom. Now let us assume we do not know the new atom that is being produced. We don't know. So let the mass number be A, and then the atomic number be Z.
Now you notice that when dealing with the second theory, according to John Dalton, we learned that an atom can neither be created nor destroyed. But hey, take note, this is under ordinary chemical reaction. Under ordinary chemical reaction. When we move on to nuclear reaction, for example, an examiner might want you to give certain differences between ordinary chemical reaction and nuclear reaction. Under nuclear reaction, atoms are usually bombarded, and even somehow through natural radioactivity, okay, you find out that the nucleus of an atom can split. When this happens, it's possible for us to get some new substances. Like in the case of this aluminium-27, if you bombard aluminium-27 that you see there with neutron particle, that aluminium will give out helium. You can see it there shown. Helium is He, then you have atomic number 2, mass number 4. Then you notice that something has been given off. What has been given off there, I labeled it as X, an atom X, mass number A, atomic number Z. You can actually calculate for the value of A and calculate for the value of Z. That's the mass number and the atomic number. It's very simple. Just your basic simple equation. On the left-hand side of that equation, you have, for aluminium, the mass number is 27. You can see that there. Mass number of aluminium is 27. Then you find out that the mass number of the neutron is 1. So on the left-hand side of the equation, you have 27 plus 1, which will give you 28, equal to the right-hand side of the equation. Helium has a mass number of 4. Then the new atom that is formed has an unknown mass number. We used A for it. So it's going to be 4 plus A on the right-hand side. On the left-hand side, you are balancing the masses. The mass number you have 27 plus 1 equal to the right-hand side, you have the mass number 4 plus A. Now, if you solve for that A, you get 28 minus 4, which of course will give you 4. So the new atom formed, X there, the mass number A is 24. You can do same for the atomic numbers. Aluminium, the atomic number is 13, as you can see there. And then for the neutron that is used in bombarding the aluminium, you find out that the atomic number there is 0. So on the left-hand side, for atomic number, you have 13 plus 0, which will give you 13, equal to the right-hand side. For helium, atomic number is 2. Then the new atom formed, the atomic number is Z. So 2 plus Z will now be equal to 13. If you solve for Z, you find out that the atomic number of that new element or new atom formed, X, is 11. And 11 is sodium. So what have we succeeded to do? We're able to bombard aluminium with a neutron particle, and we got sodium. So under nuclear reaction, it seems like we can create something new. Yeah. And that is the reason why that second atomic theory was modified. That atoms cannot be created nor destroyed. That is under ordinary chemical reaction. When you migrate to nuclear reaction, yeah, it's possible to create some things. It's possible to destroy some things. Now we're going to continue. We are done with Dalton's atomic theory number 2. What about the third one? let's just move on straight to the third one. Let's move on to the third one. Now, just did some calculation on the board there.
Cannot be destroyed.
What I explained already.
Created under a nuclear reaction, this has been modified and shows that we can actually create an atom and actually also destroy an atom.
So take note, that theory, what modifies it? Atom can neither be created nor destroyed. What modified it is a discovery of radioactivity. Because an examiner can ask you, which of the following modifies Dalton's atomic theory that atoms can neither be created nor destroyed? The discovery of nuclear reaction, radioactivity, modifies it. Listen, it's important for you to understand, we are not saying that the theory is wrong. No. What Dalton said in his atomic theory number 2, as you see showing, is correct under ordinary chemical reaction. Now, when you move on to nuclear reaction, then there is a modification there. Let us move on to the third Dalton's atomic theory.
All right. Atoms of the same element are alike in every aspect but differ from atoms of all other elements. Once again, you see that this number 3 has been starred, showing that this theory has been modified. The discovery of isotopes. The discovery of isotopes shows that atoms of the same element, in a way, may not be alike in all aspects, like Dalton proposed. Is that okay? We remember when we treated isotopes, we stated that isotopes of an element, they have the same chemical properties, but what are their physical properties? Their physical properties are different.
Good. So, that atomic theory number 3, according to John Dalton, the discovery of isotopes show clearly that atoms of the same element, they are not the same in every aspect. They are not alike in every aspect, like Dalton proposed. The discovery of isotopes modifies that theory. Like we have isotope of chlorine, chlorine 35 and chlorine 37. They do not have the same physical property. Think of their mass number. Their mass number differ. Their mass numbers differ. But these two atoms are still atoms of the element chlorine. But then their mass numbers are different. So that tells us that atoms of the same element, they are not alike in every aspect. They are not. What modified this theory? Discovery of isotopes. Now look at the fourth theory there. You can see the fourth theory. When atoms combine with other atoms, they do so in simple ratio. They do so in simple ratio. That is what we are aware of. You can think of when we have a compound like water, H2O. What is the ratio of combination of hydrogen and oxygen there? Hydrogen is 1 atom, 2 atoms. Oxygen is 1 atom. So truly, whenever atoms are combining, they combine with simple ratio whole numbers. So that theorem is still valid till today. That is why I did not asterisk it. Remember, theorem number 1, 2, 3 have been modified. Theorem number 4 still holds valid completely. Now think of this other compound where, at least if you're dealing with inorganic compounds, that particular compound, that's where you have the highest number of oxygen so far. Sodium heptaoxodichromate 6. Sodium heptaoxodichromate 6. That compound, Na subscript 2, Cr subscript 2, and then O7. The combination of those atoms takes place as simple ratios, and they are whole numbers. Sodium is 2 atoms there. Chromium is 2 atoms. Oxygen is 7 atoms. So truly, when atoms combine, right, they do so in simple ratio whole number. Then the last Dalton's atomic theorem, we have it that all chemical changes result from the combination or the separation of atoms. All chemical changes result from the what? Combination or separation of atoms. And that we also agree. This theorem is still valid. This Dalton's atomic theory still holds so true until now. Whenever you are dealing with chemical changes, what happens is that maybe an atom in a particular compound may separate from that compound to combine with another atom in another compound. Okay? So there is a separation and then subsequent combination. So chemical changes as a result of separation and combination of atoms. So that is that about Dalton's atomic theory. And remember, Dalton is known as the father of the atom. John Dalton. Now we are going to look at another concept of interest here. We now want to give attention to the discovery of our atomic particles, fundamental particles of the atom. The proton, the electron, the neutron. Let's talk about them at this point in time. Now we shall start first by asking who discovered the protons and the electrons. In each case, we are going to learn who the person is and how the person discovered these particles.
In this video, we now want to look at the discovery of electrons and protons. We want to find out the scientists that discovered electrons and protons, and of course, as much as possible, how he went about it. The scientist who discovered the electrons and the protons is J.J. Thomson. J.J. Thomson in 1897 carried out his cathode ray experiment using a discharge tube. Of course, he found out that when you subject a gas in that discharge tube under a high potential difference of about 10,000 volts, but under a low pressure, the pressure less than 10 millimeter of mercury, but of course, not as low as up to 0.01 millimeter of mercury, shouldn't be up to that. But it's less than 10 millimeter of mercury. When this condition is attained, that the gas will begin to glow, to emit rays, and when the rays are being emitted, are being produced, these rays will travel from the cathode to the anode. You can see the diagram here. This is just a simple discharge tube. Is that okay? Air is being evacuated. Air serves as an insulator. Is that okay? So it's being evacuated from the glass tube, so that we have only gas in that tube. You can see this is the connection to the vacuum tube that helps to remove air from the discharge tube.
So what is the point here? You as a student are expected to know the person that discovered protons and electrons. And simply put, without wasting time, J.J. Thomson discovered them. J.J. Thomson discovered the protons and the electrons. Take note of that. And how did he go about it? You have the simple discharge tube shown on the board here. You can see the discharge tube that is showing there. Air is being evacuated so that this experiment can work. You have a gas inside the discharge tube. The gas is ionized. And how is this being done? Look at the condition. You have to subject it to a potential difference of about 10,000 volts. That is a voltage of about 10,000 volts. What about the pressure of the gas? The pressure of the gas is expected to be low. You can see that showing on the screen, less than 10 millimeter of mercury. Although the pressure is not expected to go below 0.01 millimeter of mercury. Take note, it shouldn't go below it, but it should be less than 10 millimeters. So we can give a range. Let us say between 10 millimeter and 0.01 millimeter. Okay, so I want to take note of this. Okay, if an examiner asks you, how can you make a discharge tube to glow? How? All you have to do is to subject a gas inside it to a high potential difference of about 10,000 volts. The voltage should be about 10,000 volts. But then the pressure should be less than 10 millimeter of mercury. So the pressure is expected to be what? Low. Once this condition is satisfied, the discharge tube will begin to glow. And once the discharge tube begins to glow, what happens? Electrons will start moving from the cathode, which is the negative terminal there, to the anode, which is the positive terminal. I believe you can see that on screen, right? You can see it on screen. The discharge tube, the tube is meant to be vacuum. That is why you have to pump out air from it. You have to pump out air so it will not interfere with the electrons per se. Yes, the cathode rays that are moving. I hope it makes sense. The electrons move from the cathode and then they are attracted towards the what? Anode. Those cathode rays are what we call the electrons. And this is how J.J. Thomson discovered the electrons.
That discovered the nucleus as well as the neutrons. In this video, let us now consider the discovery of the nucleus of an atom as well as the neutron. Who discovered them? Now we're going to start with the nucleus of an atom. In the year 1911, Ernest Rutherford announced his result of alpha particle scattering experiment, from which he concluded that an atom consists of a core, and the core is known as the nucleus of an atom. So you see that Rutherford discovered the nucleus. However, there is something I'd like you to know regarding the alpha particle scattering experiment. Why this glory and honor have been given to Rutherford, it's important for us to know that two other scientists were connected to the experiment specifically. Hans Geiger, who happened to be a colleague to Ernest Rutherford, and then Ernest Marsden. Marsden at the time was the student of Ernest Rutherford. And in fact, he was given the project work of this alpha particle scattering experiment. And then he measured these angles through which these alpha particles were scattered. It was after which Hans Geiger reported to Rutherford that actually they've seen some alpha particles bouncing back to the source from which it was projected. On the bottom, we have the diagram showing the alpha particle scattering experiment. This is the source of the alpha particle. It has been shielded by lead block. Alpha particle is radioactive, so it needs to be shielded by lead block. Lead block shields them. Is that okay? Because being radioactive, can be dangerous to health.
All right, so which scientist discovered the nucleus? Simply put, Rutherford, Ernest Rutherford. The Ernest is spelled E-R-N-E-S-T, Ernest Rutherford. He discovered the nucleus. How? through the alpha particle scattering experiment. Now, it's important for you to know other contributors. Yes, an examiner can ask you a question based on that. Hans Geiger and Ernest Marsden are two other scientists that participated in that alpha scattering. The absolute mass of the proton, telling you that the proton and the neutron, they have approximate equal mass. So you expect to give attention, please, to these properties of the three fundamental components of the atom. At this point, we are going to give attention to the modified cathode ray tube. The modified cathode ray tube. But before then, quickly, please, before then, let us highlight the measurement of charge to mass ratio. The measurement of charge to mass ratio, as well as the measurement, the determination of the mass of an electron. All right. Then after that, we can now conclude with the modified cathode rays. The modified cathode ray tube, the components of that tube, what their functions are, you expected to know that. Measurement of charge to mass ratio. Who measured it? And then measurement of the charge of an electron, 1.6 times 10 to the power of minus 19. Who measured that also? We're going to give attention to it.
In this video, we now want to find out the scientists that measured the charge to mass ratio of an atom and the scientists that measured the charge of an electron. Using the modified cathode ray tube, J.J. Thomson measured the charge to mass ratio of an atom. Using this modified cathode ray tube, the value of the charge to mass ratio as measured by J.J. Thomson was given as 1.76 times 10 raised to the power 11 coulomb per kilogram. Now, who measured the charge of an electron to 1.6 times 10 raised to the power minus 19 coulomb? Aaron A. Millikan in 1910, using his oil drop experiment. He measured the magnitude of the charge of an electron to be equal to 1.6 times 10 raised to the power minus 19 coulomb. The negative sign here is simply to tell us that we're talking about electrons. Is that okay? That's just the reason we introduced negative sign there. The magnitude of the charge itself is 1.6 times 10 raised to the power minus 19 coulomb.
All right. So very clear there, is that not so? The scientists that measured the charge to mass ratio of an electron, that is, the charge of an electron divided by the mass of an electron. The scientists that measured that value, 1.676, right, times 10 to the power of 11 coulomb per kilogram. The scientist that measured that is J.J. Thomson. J.J. Thomson. He was the one that measured the charge to mass ratio. So you want to take note of that. And through what means did he measure the charge to mass ratio? He used the modified cathode ray tube. You can see the modified cathode ray tube showing on the screen. It is not the simple cathode, the simple discharge tube we saw, which J.J. Thomson used in discovering the electron and the proton. And that was just a simple discharge tube. In measuring the charge to mass ratio, he made use of the modified cathode ray tube. And then R.A. Millikan measured the magnitude of the charge of an electron. The magnitude of the charge of an electron. That value of the charge of an electron, which you know to be 1.6 times 10 to the power of minus 19 coulomb. It was R.A. Millikan that measured that. And he made use of the experiment, oil drop experiment. Oil drop experiment. That was what he used, the experiment that he used to measure the magnitude of the charge of an electron. Now, once someone knows the charge of an electron and knows the charge to mass ratio, when someone knows the charge of an electron, which of course is 1.6 times 10 to the power of minus 19 coulomb according to R.A. Millikan oil drop experiment. And you also know the value of charge to mass ratio. The E that is showing on the board here, you can see E is used to represent the charge. Then M is the mass. So if you look, so like I say, the slit, the function of the slit, excuse me, the function of the slit is to keep the electrons along their straight path. Okay? And then you have the screen, zinc sulfide. What that screen does is to help us delineate. To delineate means to help you see something. To help you see something easily. All right, so these are rays inside tube. How can we get to know that, yes, there is a ray that is actually passing, moving in the tube? To find out, we need a screen to capture the rays. And that is why we have that zinc sulfide. Once the cathode ray passes through the slit and they hit that zinc sulfide, they will ionize the zinc sulfide so that we'll now see the glowing, the light. We'll observe a bright spot telling us that, yes, there are actually rays moving in the tube. Well, as you see the tube displayed on the screen, you notice that we have 2 points on that zinc sulfide screen. Point A, which is the straight path where the rays will hit first. Then I have a curve to point B as a result of the deflection of the beams of electron by the field. As a result of deflection. And once there is a deflection, you have a circular path, radius will come in. There are 3 forces actually acting in this tube. We have the centrifugal force, we have the magnetic force, and we have the electric force. These 3 forces can actually be resolved under a condition of equilibrium. When they balance, we can resolve it to calculate the velocity of the electrons in this cathode ray tube. And that can help us to actually know what the velocity of an electron is whenever the electron is moving in a given field. If you expose it to a magnetic and electric field, what will happen? This relationship between magnetic force, electric force, and centrifugal force can actually help us to calculate this velocity. And of course, I'm going to hold a special class on that. So you learn more about these equations. All right, you learn more about these equations. You can take a look at equation 6 asterisk. Look at that equation 6. V equal to E over B. That E is electric field in the unit of Newton per coulomb or in the unit of volt per meter. And then we have B. Our B is magnetic field in the unit of Tesla. In the unit of what? Tesla. Yeah, instead of Tesla, we can use Weber per square meter. So you can just look at that equation 6 asterisk. If we know the value of electric field, also called electric field intensity, and we know the value of magnetic field, also known as magnetic flux density, we can actually calculate the velocity of an electron in a field, simply dividing the electric field by the what? Magnetic field. All right. So this is much about this concept of development of atomic theory. I'm going to take you through to certain questions that I quizzed, our students through in our WhatsApp group. From what we have gathered so far from this class, I would like us to go give answers to those questions. I would like us to give answers to some of those questions. So let us see what we have. All right, so we have the following questions here. The first question is, the following scientists were involved in the alpha particle scattering experiment. Is that the first question? Let me check. Oh, no, that's not the first question. Good. So here we have the first question. The nucleus was discovered by Dash through Dash experiment. So the nucleus was discovered by Ernest Rutherford by the alpha particle scattering experiment. So the correct option is C, and I'm going to click on the option. You would see about 6 persons got the answer correctly. Those who went for A, J.J. Thomson, modified cathode ray tube. Thank you for attempting, but that is incorrect. The next question we have, the following scientists were involved in the alpha particle scattering experiment. Now, there were 3 scientists that we identified. One of them is Ernest Rutherford. The other is Hans Geiger. And then we have Ernest Marsden. The correct answer is option D. The next question we have, a discharge tube glows when it is subjected to A, high pressure and low temperature. That is not the answer. B, high potential difference and low pressure. That is the correct answer. We move on to the next question. Let me try to approve someone who requests to join. Okay, the next question we have here is, Dash scientists discovered proton. The correct answer is J.J. Thomson. I don't know what's wrong with, this power holding company. They're always known for that. J.J. Thomson. We'll move on to the next question. Which of the following Dalton's atomic theory was modified by the discovery of isotopes? Option A, atom cannot be destroyed, cannot be created nor destroyed. That is not the theorem. Option B, chemical change is as a result of separation or combination of atom. That is not the option. We have option C, atom is the smallest indivisible particle. No. Option D, atoms of the same element are alike in every aspect but different from atoms of other elements. That's the correct answer. That theory has been modified. It was modified as a result of the discovery of isotopes. Next question. One of these is not a property of cathode rays. Option A, they travel along a straight line. That is a property. Option B, they do not possess kinetic energy. That option is not a property of cathode rays, because cathode rays, they possess kinetic energy. So saying that they do not possess, it means it is not a property. So the correct option is B. The others are definitely properties. Next question. The function of zinc sulfide in a modified cathode ray tube is The function of zinc sulfide in modified cathode ray tube is for easy ionization of the cathode ray. No, that's not the answer. Majority that answered that, they went for that option, but it's incorrect. Option B, to react with the cathode rays. That is wrong. Option C, to attract the cathode rays to the available field. That is wrong. Option D, for delineation of the cathode rays. That's the correct option. The function of zinc sulfide is to help us to easily delineate, to see, to observe, to behold that yes, there are rays actually in that tube. So those rays are captured, all right? They form bright spots on the zinc sulfide. That is why we use that zinc sulfide there. The father of the atom is A, GMAETS 41, B, Faraday, C, Dalton. Dalton is the correct answer. D, Davido. The correct answer is Dalton. All right. Next question. The absolute mass of the electron is. The absolute mass of the electron is. We have those options there, and the correct answer is 9.1 times 10 to the power of minus 31 kilogram. That's option D. Next question. One of the following scientists measured the charge to mass ratio of the electron. One of the following scientists measured the charge to mass ratio of the electrons. The scientist that did that is J.J. Thomson. That's option B. Next question. Dash experiment was used to determine the magnitude of the charge of an electron. The correct option is option D, oil drop experiment. Move on to the next question. The slit in the modified cathode ray is for dash. The slit in the modified cathode ray is for dash. A, focusing the streams of ray on the screen. That is the correct answer, to focus the streams of ray on the screen. So it gives it a straight line movement, okay? Directional movement. That's the function of the slit. So option A is correct. It is not for attracting the rays from the cathode. It is the perforated anode that attracts the ray. As regards option D, the option C rather, okay? But that is not the work of the slit. This takes us to the next question. The velocity V of electron under the action of magnetic field 10 Tesla and electric field 5 volts per meter. The velocity is what? The correct answer is option A, 0.5 meter per second. Recall that the velocity of the electron under the action of electric and magnetic field is equal to the electric field divided by the magnetic field. The electric field here is 5 volts per meter. The magnetic field is 10 Tesla. So divide 5 by 10, you get 0.5 meter per second. So the correct option is option A. And of course, this is how we've come to the end of this class. And I hope that those of you that connected, you've learned something good. You've learned something good. And at least you've been directed to area of likely exam questions on this topic. It's all right. I am going to hold a class where I will solve more questions on this charge to mass ratio and velocity of an electron in a field, okay? I'm going to release a video on that, just a short video on that. To have a wonderful night rest. Good night.